Yep, seems to be working. Okay. What's the resistance of that? Easy. What's the resistance of it? R1 is the resistance of it. Numbers are silly, okay? I think we all know that from going beyond high school maths. You don't mess about with numbers anymore, you mess about with symbols, right? Why would you want to? R1 could be 3.712893 ohms. And it's meaningless, right? R1. What's the resistance of that? What's the resistance of it?
What was the question?
What's the resistance of the one on the bottom, the symbol
The
on the bottom?
capacitor,
Yeah.
well, it doesn't have a resistance like an impedance.
Good answer.
It has an impedance in AC.
It doesn't have a resistance. How does something not have a resistance? It has a characteristic resistance, which is kind of the resistance of the pins and all the rest of it, the manufacturing process. But resistance is something, think about what resistance is. Resistance doesn't change as a function of frequency, it's constant. Okay? So I've got a 1K resistor and I feed 1000 hertz into it. I get the same amount of resistance if I feed a megahertz in. Frequency doesn't make any difference. That's what resistance is. But there's kind of a AC equivalent of called impedance. Well, for a resistor, resistance is equal to impedance. So what is impedance? It's the AC equivalent of resistance. It's just different words for the same thing. So can a resistor have impedance? Yes, it can. But for a perfect resistor, it's exactly the same as its resistance. This will have, unfortunately, a little bit of capacitance, a little bit of inductance. This is where circuit theory gets really complicated and quite advanced. But for all intents and purposes, that resistor has no impedance, or that resistance just has pure resistance, and its resistance is equal to its impedance. In other words, it doesn't matter what frequency I fire through it, it behaves the same. This one here, that's not true. So its AC resistance, or its impedance, is a function of frequency. Now, a function of, what does that mean? Well, it just means that you've got something which is acting on it. A function of. So if you've got a cup of coffee and I come and drink half of it, that's a function of one half of your coffee after it's drunk, right? It's a function of. It's a thing, you've done something to it, right? So what that means is that the impedance changes as a function of frequency. Now for two things which are, so resistance has an impedance, yes it does. But resistance is not reactive. In other words, it doesn't change as a function of frequency. A capacitor is reactive. And its counterpart, the reason we say it's a counterpart is kind of the opposite. That is reactive to it. Changes as a function of frequency. It's impedance, the kind of resistance that we see. So if I fire 1000 capacitor, I can calculate its equivalent resistance, but it's called impedance. Okay? Now, wouldn't it be useful if I could have an equation that would say the impedance, and instead of writing R now, we write it in X, and it's to do with the inductor, so we can use the subscript L if we want. You don't need the L there at all, really, but I'm going to put it there. So, what is the equivalent resistance of an inductor? Well, probably seen it before in physics, actually. 2 pi F L. So that means that if you give me an inductor and tell me what size it is, and the inductance is in a unit called henries, if you tell me what size that inductor is in henries, I can tell you, if you tell me the frequency as well, so I need 2 pieces of information here. I need how big it is in henries, and I need what frequency you're going to operate it at. 2 pi doesn't change, so therefore I can calculate the impedance or the equivalent resistance at that frequency. Change the frequency, the impedance changes. Now it's kind of complementary one, which I'm going to call XC, which is the impedance of the capacitor, is actually just this. So it's just the opposite of it. X to the minus 1 upon, whichever way around you want to look at that. So that one there, what does that tell me? Well, straight away, you should never go into that and just start calculating. It's pointless. Because what you want is ballpark. So what happens, forget capacitance, it's fixed, right? What happens if I increase frequency?
It's inversely proportional.
That's
If
right.
I have 5 frequencies, I have low impedance. If I have low frequency,
Excellent. So in the top one here, if I increase frequency, means a bigger number divides it. Yeah. Which means well, that's what I'm saying. So F gets big. What's 1 upon big? Little, right? So 1 upon big is little. So if I make the frequency big, 1 upon big is little, so that means that the impedance is small. In other words, it conducts. Yeah? If I take this one here, and I make the frequency big, if I make that big, then this must get big. So as I increase the frequency, the impedance gets bigger. So in other words, one's the opposite of the other. Do you see what I mean? Yeah? So you've got these 2 wonderful equations. For the capacitor, the equivalent impedance, and the inductor, the equivalent impedance. Why would you want to know that for? Well, remember the circuit on the board. Because now what I can do, is I can just replace one of those with one of those impedances, and as long as I do the calculations right, in other words I know the input frequency, I can predict what the I'm using the word resistance, I can predict what the impedance is at that frequency. So therefore I can predict what the height of the output waveform is. For something that changes according to frequency, that's really clever if you think about it. Yeah? Okay, so let's do that in mechanical ways now. So I'm just going to leave the equations on there. But let's extend our knowledge a little bit now, because we know that capacitive reactance, if frequency is high, then it conducts. 1 upon big is tiny. And for an inductor, if we make the frequency high, that means the reactance is also high. It's a big resistor. Okay. Right, what would happen if same circuit as we had before, but instead of there being a resistor there, I'm still going to call them R, I'm going to call that R1, I'm going to call that one R2. That's not right, I know that. I'm just going to do that for convenience. That's the in, that's the out. What changes? What changes? Nothing changes, because I've got an equation for the capacitive reactance of it. So all I've got to do is replace this here with its equivalent resistance, which is 1.25. If I replace that with that, I can treat it exactly the same way as I could the two resistors. Except now I'm dealing with those two. Now I don't know what the frequency is, because I haven't defined what the frequency is. It could be anything. But the rules stay. So I'm using the same set of rules to achieve something which is going to produce a very, well, literally complex, but I don't mean as in complex numbers, but it is complex numbers. I'm going to produce something which behaves differently at different frequencies. So instead of having 5 volts, 3 volts, whatever it was out here, I can't say for sure what it is until you tell me what the frequency is. The capacitance to a lesser extent, because it's fixed across all experiments, but if I know the frequency, I can predict what the output's going to look like. Well, that's magic, because now I can do things that other people can't do. Mere mortals can't do this, because they don't understand these little subtleties attached to it. Now, what happens if I put, let's just draw it like this, so if I put low frequency in here, what do you think the output's going to look like? We're not talking about 10 hertz, 100 hertz, million hertz. If I put low frequency in here, what's the output going to look like here? Is it going to have a small amplitude or a big amplitude? You're all right, but why a bigger amplitude? Well, because this effectively isn't here, is it? Because you've got 1 over big, you've got 1 over small, which is also, which is big, so therefore all of what was here makes it to the output. What happens if I make the wave here high in frequency? Well, you've got 1 upon big, which is small, which means that effectively this becomes a short circuit. Yeah. So, what have I got? I've got a graph, if I do these two extremes, at high frequency, the output goes to 0. At low frequency, the input voltage, or the output voltage rather, is a maximum. So it doesn't look exactly like this, but it's very, very tempting just to do that and say that's how that behaves. As frequency increases, the output increases in the circuit. Okay? That's just from the numbers. So we haven't plugged any numbers in, we're just using algebraic equations. And yet we can derive this, which tells us this circuit at high frequencies, the output's next to nothing, and at low frequencies, the amplitude is very high. Anyone know what that's called? The general class of things that belongs to is called? Filter?
Well, what's the question?
What's the general class of circuits which belong to this?
Oh, that's high testing, right?
That one's a low pass.
Well, yeah,
It's passing the low frequency and blocking the high frequency. It's a filter. Filters are magic things. So on a telephone, if you haven't got filters in there, when you're talking to someone, there will be a high-pitched scream in your ear all the time, because that's generated by the wires and all the noise and lighting and everything around. You can just filter it out just using it. the same reasoning to inductors, which I will do in a little while, but what I suggest that we do first is we run the simulation of multi-sim and you see for yourself whether I'm telling you the truth or not, yeah? Okay, let's do that then.